Is that me or Charles?
All of the above.
Okay, so we're all El Nerdo?
Yes.
All right.
It's a big collective.
We are the Albertos. Like the three amigos, but
It's the four El Nerdos.
I'm also, if you can
symbol.
sitting in a chair.
which number? Who gets what number?
Okay, so let's talk about, let's start with the free response question on that one. So, let's talk about this whole concept of when you can have hydrogen bonding and when you can't, okay? So the first criteria to have hydrogen bonding is, first off, understand that this is not an intramolecular force. It is an intermolecular force. So this is going to be a force that holds molecules together. It makes them sticky, okay? Which is a horribly non-scientific term, but you get the visual. So the stickier it is, the easier it is to change it into a liquid. If it's really, really sticky, it's a solid, okay? Things that aren't sticky exist as gases. So thankfully, nitrogen and oxygen, which make up the vast majority of our atmosphere, aren't very sticky. That's why we have an atmosphere of gases. And thankfully, the boiling point of, say, for example, nitrogen isn't like, 28 degrees Fahrenheit. If nitrogen condensed to a liquid of 28 degrees Fahrenheit, which it doesn't, thank God, then when the temperature dropped to 28, it would literally rain liquid nitrogen, okay? And then our atmosphere would be turned into a vacuum and bad things would happen, okay? We wouldn't be here having this discussion. So one of the things I don't worry about is like, oh, it got so cold it's going to rain oxygen or nitrogen. It's not going to happen. Now, so first off, that's the first thing. Understand what it is. The other criteria is that to have nitrogen bonding, you have to have one of three elements: nitrogen, oxygen, and fluorine. Not. So, from an electronegativity standpoint, here's what happens. Let's say fluorine is kind of the ultimate example. So, how many valence electrons does fluorine have?
7.
The fact that there was hesitation at all, a room full of AP chemistry students, how many valence electrons does fluorine have? Crickets. That's what I heard.
We're like a week of school left.
Do you want to get the number?
We're like 3 days out from the exam.
Yeah.
7
7.
and a half
Seven.
days
7.
left.
This many.
I'm so
Thank you.
7
Okay.
and a half days of school left.
Does fluorine have a high electronegativity or a low electronegativity?
Extremely high.
Extremely high, because it has 7, and which energy level is it filling?
Second.
The second.
Like literally the strongest.
So here's what happens, is that you have to understand what happens within that to understand hydrogen bonding. So if you have HF somewhere in this molecule, the hydrogen has to be directly attached to the fluorine. If the hydrogen, if let's say for example you have a carbon, a hydrogen, a hydrogen, a hydrogen, and a fluorine, okay? Let's say you have this structure. This would not be hydrogen bonding. Even though there is a fluorine and there's a hydrogen within that compound, you're not going to have hydrogen bonding because the fluorine isn't directly bounded to the hydrogen. So just because you have hydrogen or fluorine, hydrogen or oxygen within a molecule, that doesn't mean that you're going to have hydrogen bonding. They have to be bound up with each other, and here's the reason why. So this fluorine has a very, very high electronegativity. It has 7 valence electrons. So it's going to take that electron from that hydrogen, and the fluorine then is going to end up being negatively charged, and the hydrogen is going to end up being positively charged. So this basically only works when you have elements, and if you notice, they're in sequence: nitrogen, oxygen, fluorine. Because those have enough electronegativity to pull the electron from the hydrogen so that you create a polar situation where you have negatively charged and a positively charged. Okay, so this is why water has hydrogen bonding. So, what the point of the story is that you're going to create something that has a positive charge and you're going to have something that has a negative charge. So if you look at water, okay, so water's like the poster child for this situation. It fulfills the criteria because you have oxygen. Oxygen has a high electronegativity. It means it wants to take in electrons. So it's got this dome of negativity with the excess pairs of electrons. Then down here, the hydrogen end is positive. So you have hydrogen bonding with water, not because the hydrogen bond is not with the oxygen and the hydrogen. The hydrogen bond occurs when you bring another water molecule close to it. So the hydrogen bond, this is why it's called an intermolecular force. So you have a negative end of this oxygen molecule. That's going to be attracted to the positive end of the next water molecule beside it. That's where the hydrogen bonding occurs, okay? It is not, this is the most common misconception about hydrogen bonding. Oh, it's it's between the hydrogen and the oxygen itself. That is not it. It occurs between the oxygen on one water molecule and the hydrogen end on the other one, okay? So get that out of your minds right now. So on this question, on B where it says, hey, draw one dashed line to indicate a possible location of a hydrogen bond. There's any number of ones that you could draw on that structure. So because of the fact that you're given the structure of urea, so for example, if you look at that where you have nitrogen, couple of electrons, hydrogen, carbon, double bond, oxygen, nitrogen, hydrogen, okay? So if this situation you have water, so one of the things about things that dissolve is that likes dissolve likes, okay? So urea is polar. It has hydrogen bonding. It has a dipole. So that means if you put it in a solution that has those same characteristics, it's going to dissolve in it. So you all have seen, like you drop a piece of magnesium in hydrochloric acid, and you make hydrogen gas. Okay, the hydrogen gas doesn't get dissolved into the water because the hydrogen gas is a completely different type of structure than water molecules are. That's why hydrogen doesn't dissolve in water. Ammonia does, because ammonia is a similar type structure. So you bring in a water molecule here. So one option where you can have hydrogen bonding is that you could have hydrogen bonding between this oxygen and that hydrogen. That's a possibility, okay? Now, what you can't do is you can't, for example, you've got this lone oxygen up there. That won't be hydrogen bonding because of the fact that the hydrogen isn't bound up to that nitrogen. So you could have hydrogen bonding on that end because there's a nitrogen directly attached to that. So any place there's basically the negative end of that oxygen molecule on the water can bound to any hydrogen on the other side of that. Okay, does that make sense? So do not think hydrogen bonding occurs within the water. It occurs within water molecules. Cool with that? So, what do you have as your hybridization on 1A?
SP2.
SP2. There you go. Three reasons high electron density. Your answer to C, where you calculate that molarity, that one should be something pretty close to your current age. Hopefully no one's going 0.1.
Wait a second, I didn't know I was 99 years old.
Go thing.
Now, so the student also determines concentration in K. Based on this solution, urea endothermic or exothermic justify your answer. So you have a saturated solution of 20 degrees, concentration of urea in a saturated solution 19.8. So is the solution endothermic or exothermic in terms of Le Chatelier's principle? So here's the deal. So Le Chatelier's principle, if you go through the entire AP test, and they don't say something about Le Chatelier's principle, I'd be surprised. It has been known to happen, but not very often. So Le Chatelier's principle basically says, hey, if you stress the system, it responds to the stress. Okay, so if you have an equation and you have reactants and you put more reactants in, it's going to stress it and it's going to make more products. If you remove a reactant and it can reach a point of equilibrium, then it can shift back the other way. So if you look at this one, so this reaction is going to be endothermic, mainly because of the fact that when you stress it, okay, in effect that when you add that heat, and the whole key to this is at night, if you raise that temperature from 20 to 25, the molarity goes up. So that means that it can hold more, can become more concentrated at higher temperatures. So if you had added heat and that molarity had gone down, that would have meant that it was exothermic. So this process is endothermic. So you warm it up, you're basically saying, hey, and if you look at the dissolution process, your products are ions. So when you warm it up and you can hold more ions, you have shifted that to the product side. So that means it's an endothermic reaction because you add the heat, it's endothermic, it's going to become more concentrated and it can hold more in it. Okay. So on E, just you're trying to figure out the specific measurements and you're trying to find the value of the molar heat solution for urea. So this is another thing where he kind of goes old school. So at the end of the day, what do you need to determine the molar heat capacity? What are some things you need to measure?
Mass, volume of the
Mass, temperature, those are really the big things, right? Because if you can measure mass and temperature, you can calculate Q. And then if you divide that by the number of moles, hey, boom, there you go. So you just need to say something like, hey, we're going to measure the initial temperature, we're going to measure the mass of what's going to be added, we're going to find the temperature, we're going to calculate the value of Q, and then from there we can divide that by the moles to get that value. So let's talk about F. So you've got your solid is 104.6. So let's just think big idea. Before you do any calculations at all, is that S value, comparing it to an aqueous value, is your answer going to be bigger or smaller than 104.6? 1G.
Sorry, I was looking at a different question. What did you ask?
Okay, so on that back side,
Yes, F is what.
it has an S value for the solid of 104.6.
Yes.
We're going to try and find the S value of the aqueous after it's dissolved. So do you think the entropy value is going to be bigger or smaller than 104.6?
Bigger
Why?
because it's a liquid now. It's a
Yes,
solid.
you've gone from locked up into a solid structure into a solution where it can move around, okay? And again, you're focusing on that. The water technically is going to have less entropy because it's got to drag around these molecules, but the entropy itself of that value is going to increase. So your answer on F should be around 170. Okay? And then basically that's the answer to G. using the particle left seems like is positive for the dissolution of water in urea, because of the fact that you're going from a solid into a liquid, and there's more ways it can move around. Now, so look at this. Then you get to H, and this is the bigger question when you get to H. You know, delta G equals delta H minus T delta S, okay? So, what's this, based upon where we're at right now, what's the sign of delta H? Positive or negative? Positive, because we said it was endothermic, right? So, here's a logic problem. Could the delta S be a negative value and have this reaction take place?
No,
Why?
because you never get a negative delta G.
Yeah, you would never ever get a spontaneous reaction. So here's like a scenario. As soon as you're told a reaction is endothermic, but yet the reaction still happens, the only way it can happen is if you still have a positive delta S. So as soon as you see this, okay, hey, great, positive delta H, you know the delta S has to be positive. Because if it didn't, this stuff would never dissolve, okay? So basically what's going to happen is you're going to have minus T delta S. So this is temperature dependent. Sydney, is the temperature dependent on high temperatures or low temperatures?
High temperatures,
Why?
because you have to be higher than whatever your H value is when you multiply your temperature by your S value.
Beautiful answer. Couldn't be better. So, since you're subtracting that T delta S value, that T delta S value has to be bigger than your delta H value so that you end up with a negative delta G. Okay? Makes sense. We're good on that one. Everybody's cool. All right. So, on the questions out of the book. So basically, these are all questions about London dispersion forces. So let me talk about one of them. And when you go to answer these questions, if you're taking the AP test, let me see some of this book. Let me see my book. Give me my book.
Happy birthday.
Thank you.
So
Merry
welcome.
Christmas.
Thank you. Happy Hanukkah. Jeez.
Okay. So, what page is this on? 462. Yeah, okay. So, if you look on, and this is just kind of the technical side of how you answer this question. So you got ethylene glycol, da-da-da-da-da, antifreeze has an melting point of 198 degrees Celsius. So if you understand how antifreeze works, basically it keeps the water in your car from boiling. It also keeps the water, more importantly, it also keeps the water in your car's engine from freezing when it gets down to very cold temperatures. Yeah, Sean?
I'm getting the PDF for the book.
Huh?
I don't have the book. I don't have the book, so I'm trying to get it online.
Here, we have an extra book.
Nice, thank you. So, if here's an automotive tip. If you have to if it's going into winter, and this is why people say, hey, check your antifreeze. What does water do when it freezes? It expands. And if you have pure water in the radiator of your car, the water's going to freeze and it will actually crack the engine block on your car, and then your engine is ruined. Okay? So this is why people say, hey, check your antifreeze level. That's what you need to do. Okay? Because otherwise it's going to freeze. So if you look at these structures, it says Y replacement of a hydrogen on the oxygen generally results on a lower boiling point. Now, what's the relationship between a lower boiling point, so you're going to lower the boiling point, and the strength of your intermolecular forces? So if you have a lower boiling point, are your intermolecular forces stronger or weaker?
Weaker.
Weaker. So here's the relationship. Lower the boiling point, the less sticky it is. That means it's easier for it to change from a liquid into a gas. Now, in contrast that, and this is what we talked briefly about yesterday, there's something known as vapor pressure. So if you have a lower vapor pressure, remember, understand how vapor pressure is created. Vapor pressure is created by putting a substance into a container and then measuring over a period of time what happens to the pressure inside of there created by those particles turning into a vapor, hence the term vapor pressure, okay? So if you have lower vapor pressure, does that indicate stronger intermolecular forces or weaker intermolecular forces?
Stronger.
Stronger, because that means with the lower vapor pressure, what you're saying is that these particles aren't breaking free as easily. They're more sticky, so you don't get as many as out there in the vacuum creating pressure. So on that one, it explains why the replacement of hydrogen on the oxygen by CH3. So once you replace hydrogen on that oxygen, what do you no longer have?
Hydrogen bonding.
You no longer have hydrogen bonding. Are you still going to have London dispersion forces?
Yes.
Yes. You're still going to have London dispersion forces because you have an electron cloud. Now, then it says, what are the two major factors responsible for the difference in the boiling points of the two ethers? Okay? So, when you look at how you're going to, if they ask you a question like this on the test, if you're ever asked about and comparing London dispersion forces specifically, just don't say, oh, it has a stronger London dispersion force. It's not how you want to answer the question. You need to articulate that by saying, hey, it has a bigger electron cloud, therefore it's easier to induce a temporary dipole moment. If you really want to get fancy, okay, you can say if you have stronger London dispersion forces, you can say it has a higher degree. This is the fancy version of this.
No, this is called these are the fancy.
You can say it has a higher degree of polarizability. What that means is that it's a bigger electron cloud. You're going to induce a situation where the electrons get shifted, and you're going to have one region that's negatively charged and another region that's positively charged. So a higher degree of polarizability, this is like the fancy way of saying, hey, you got a big electron cloud and we're going to induce a dipole moment. Okay, so that's the fancy way of saying that. On that question on 25, if there's anything that, if you're taking the AP test, that you memorize and that's that answer to 25A, what atoms must the molecule contain to participate in hydrogen bonding, and what are those three?
No.
Knife. Nitrogen, that's also how you spell knife, or say knife if you're south of the Mason-Dixon line. I got a knof. No, that's true.
Thank you for the insight.
Anyway, yeah, just, and it's spelled K-N-O-F. Weird.
Can we talk about 16?
Okay,
Not 16, 18.
Yes.
what about 18?
Can we talk about it?
All of it.
Yeah, we can talk about it.
Yes, please.
What are the answers
I don't know.
for A, B, C, and D?
Do A and B rhyme with hydrogen bonds? A and B.
Okay.
Oh, what? I only got one.
One
Okay,
is hydrogen bond?
Just A.
so,
A is the only one.
okay, so you've got ethyl alcohol, CH3OH, and CH3 boils at 6. So, start with this idea. which ones on 18A, which one is stickier?
CH3OH.
How do you know?
Hydrogen bonds. OH. Tyler Boyd.
How do you know it's stickier?
Boyd.
The boiling point. It has a higher boiling point. Therefore, it's stickier. So, if you notice on the structure, what's the only difference between the CH3OH and the CH3SH?
OH instead of an SH.
Yes, so the CH3OH has hydrogen bonding, but the other one doesn't.
That's what I understood. I didn't understand B, C, or D.
Oh, minor. Okay. So on B, xenon is a liquid at atmospheric pressure, whereas argon is a gas. So look, where are they at on the periodic table?
No gases?
Which one's below which?
Xenon is farther down.
Xenon is farther down. So which one has the bigger electron cloud? So with the bigger electron cloud, it's easier to induce a dipole moment, therefore, now. What did you say?
Current.
Current.
Word, you broke us. You broke
This is
us.
what you've done.
I know. Try teaching it and keeping it all straight.
No,
Okay.
absolutely not. I still see.
So, is it possible for xenon and argon, pure samples of those, to have hydrogen bonding?
No.
No. Is it possible for them to have, if you think this through, a dipole-dipole bonding?
Yes.
Can argon and xenon, any of the noble gases,
No.
have dipole-dipole bonding?
No.
Charles, you shake your head. Jacob, you shake your head no.
Because they're both, like, they can't really be charged because
Why?
they have full electron shells.
Yes, they're the Gapshons of the classroom, okay?
That's wrong.
The only way you can have dipole-dipole is if you have a non-symmetrical structure. These are perfectly symmetrical. These are why they are the noble gases. This is why they're called noble gases and not the noble liquids. Okay?
You know, I've never actually thought about that before.
That is crazy. I didn't even think about it. My bad. You learn something new every day.
If we were to put it together, what do we learn?
Oh, well
gases,
here,
gases.
let's look at the alkali metals.
Always or just something?
Okay? Alkali metals.
Oh my god, what are they?
Wait,
Oh, I don't know, metals.
is that the second column?
But are they solids though?
The first column. The second
Oh,
column.
wait.
is the
Alkali
alkali
metals?
metals.
I thought you were talking about noble gases, sorry.
Metals exist.
Yeah, but it's
Hydrogen's
not.
not a part of the alkali.
It's not a part of the alkali metals.
Which one is it? Hydrogen is
Or what is hydrogen considered?
Huh?
What is hydrogen
technically
considered?
a
It
halogen.
really isn't. It's just like an off-liner.
So it's just hydrogen and then all the others? Okay.
Not you.
Okay. Anyway, so now, so krypton boils at 120.9, chlorine boils at 283. So, where's krypton at? Is it a noble gas? Where is it out of the periodic table?
Noble gas.
It's a noble gas. Okay? But now you have CO2. CO2 is a gas, right? Means it has a high degree of entropy. Which one's going to have more electrons around it?
Thank you.
Krypton.
Krypton or the chlorine? Okay? But if you notice, chlorine has a boiling point of 283 or 238. And the reason is because you have two chlorine atoms hooked together. So you have two, if you think about this, you have two of these hooked together. Krypton, when they run into each other, you're only running into like marbles, basically. They're just going to bounce off of each other. The chlorine, because of the fact that it's more linear, is because what's going to make that then a stronger London dispersion force is because when those run into each other, there's more surface area of those electron clouds. it's easier to induce a dipole moment. So that's why the Cl2 has a higher boiling point than the Cr does. Okay? Because again, that's the only game in town is London dispersion forces. You don't have anything else. Okay? Does that,
What about there's,
okay?
so I thought it was hydrogen bonds.
So
Like Kevin confused me.
if you look at acetone, okay? Y'all have dealt with acetone. Where should you all use acetone?
They have polymers.
No.
My fingers.
I do not do my nails.
My toes. Most of my toes. You gotta get that stuff off.
I now agree that that's
It's like teaching AP chemistry in Arkansas.
Now I think we're talking about
Okay,
labs
that.
rather
You
than
always
my
like-
personal application.
Yeah, you said
Always
we all
rose
see acetone.
Not
My finger.
I said you all, including like everybody in the room.
Who
I
say that
painted
they
my-
can't paint their nails?
I painted my
You don't
brother's
know what
nails.
people do on
Your
their
son
first
really
day.
painted his nails before.
Okay, everyone including me.
Have you never painted your nails before?
Do you even know me?
Not once in your life have you ever painted your
Do
nails.
you know me?
Not even on Willis.
You have so many. I'll
Do
give you
you
20 bucks.
know me?
You have so many sisters. I'll give you 20 bucks.
Yeah, I feel like your sisters had to have
I
painted your
painted
nails
my
at
brother's
some
nails.
point. No.
Okay, so beyond taking off nail polish, where did you use acetone?
Soaking off the tips as well.
Pretty sure we used it for one of the labs.
One of the labs.
Wait, we,
I
what?
couldn't tell you which one, but
It was a while ago.
We've used it in
it
last.
smelled pretty strong.
Yeah, then we use it.
Yeah, it's probably.
Yes, the iodine lab.
Oh, yeah.
That's right.
Oh, yeah. Acetone, iodine, hydrochloric acid. Yeah.
Oh,
How did acetone exist?
Liquid.
As a liquid. But you can smell it, right?
Yeah, it's
stanky.
So what does that mean? Do you think it's easily turning into a liquid or not?
Yeah.
Oh, it easily turns into a liquid because you can smell it. So here's the whole quick lesson on perfume. If you want, what do perfumes have to be able to do? Exist as liquid or volatilize into a gas? Because if they stayed as liquid, guess what? You could never smell it. Okay? Well, you'd be soggy.
That's what I was thinking.
If
Yeah,
you
comfortable.
Yeah.
Oh, I like your new
So-
perfume. It looks really.
Really nice.
So here's a quick question. So if you look at the structure of acetone, CH3, 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 double bond, oxygen. These are all hydrogens here. These are all hydrogens here.
I see that.
Does acetone have hydrogen bonding? Does acetone have hydrogen bonding?
No.
Why not?
No.
There's hydrogen and oxygen.
There's
The
not.
hydrogen's not the.
Ah, the hydrogen is not bound directly to the oxygen.
It's not nothing.
So it's not hydrogen bonding.
I'm going.
But acetone has a dipole moment. Which direction would the arrow point for the dipole moment on acetone? Yes. So that's going to have a dipole moment. So what that would mean is that then if you bring another acetone near it, you can have dipole-dipole bonding based upon difference in basically your electron structure.
Yes.
Does that make sense? On 20, you should have 3 statements that are true.
Let's go, baby.
Okay,
I would had to go
Because I got.
are we good?
horrible time.
True, false, true.
I think we're good, Berg.
So
Oh, hold on, I
staple
did-
the
hold on.
what?
I did have one on 2A3.
What?
On 2A3,
Two.
we only talked about dipole, but when I looked it up, it said there was such a thing as ion dipole. What did you want there?
Don't worry about that. That's if you have like a calcium ion attached to like a water molecule.
Okay.
So,
That-
Wait, which one is sodium?
okay, are we good? Once, twice. So here's what I want. I want the yellow sheet on top. Then the answers that go with the yellow sheet, and then the questions from the book. So yellow sheet, answers to the yellow sheet, questions from the book. Okay?
What up?
And please pay attention to how you staple them.
I put
I'm excited.
over the ion dipole, dipole, dipole.
Actually,